Have you ever stared up at the night sky and wondered if someone, somewhere, is looking back? With billions of stars overhead and even more planets circling them, the odds say we shouldn't be alone. Yet, every time we listen, all we hear is silence so deep it almost feels impossible. What if that silence is the universe's biggest secret, or its most urgent warning? If you find yourself haunted by these questions, you're in the right place. We're about to explore the most mind-bending theories, the wildest possibilities, and the latest science behind the greatest mystery of all. Where is everybody? If you're ready to dive into the unknown, make sure to subscribe and turn on notifications. You won't want to miss what comes next. Every night, as you look up, the sky is filled with countless stars, each one shining down in utter silence. Astronomers have determined that, just in our own galaxy, there are more planets than there are grains of sand on all the beaches of Earth. The numbers are staggering. Statistically, the universe should be teeming with intelligent life, yet, when we listen, we hear nothing, no signals, no visitors, not even a hint that someone else is out there. The silence is so profound, it almost feels impossible. Tonight, let's journey through the most serious explanations scientists have offered for this cosmic quiet. We'll explore ideas ranging from galaxy-wide extinction events, to civilizations hiding in fear, to the unsettling thought that perhaps we are the very first intelligent beings to ever ask, are we alone? If these questions keep you awake at night, you're not alone. Get ready, because we're about to dive in. The universe is ancient, about 13.8 billion years old. In that immense span of time, stars have formed, planets have cooled, and the basic ingredients for life have been scattered across hundreds of billions of galaxies. The math isn't complicated. It overwhelmingly suggests that life should have arisen countless times, in countless places, long before humans ever existed. Yet, every time we point our telescopes at the sky, we get the same answer: silence. This is the heart of what's known as the Fermi Paradox, named after physicist Enrico Fermi. In 1950, he asked a question so simple that it still haunts scientists today. If the universe is this old, this vast, and the chemistry of life seems so straightforward, then where is everybody? What makes this question so disturbing isn't just the lack of a radio signal from a distant world. It's the complete absence of any evidence. No artifacts, no massive structures, no engineered signals. In a universe this immense, this ancient, and this chemically rich, we should see signs of life everywhere. Instead, it looks empty. To really grasp the weight of this silence, consider the scale. Our galaxy alone contains somewhere between 200 and 400 billion stars. Most of those stars have planets. A significant number of those planets are in what scientists call the habitable zone, the region where liquid water could exist on the surface. If even 1 in a million of those planets developed intelligent life, our galaxy alone would be home to hundreds of thousands of civilizations, many of them millions of years older than us. Imagine a civilization just 1 million years ahead of humanity. With even slightly more advanced technology, they would have had time to explore every corner of the galaxy, many times over. The real question isn't just, where are the aliens? It's, why hasn't anything reached us? No probes, no transmissions, no evidence of engineered objects drifting through our solar system. That absence demands an explanation. Over the years, scientists have proposed dozens of possible answers. Some are comforting, but most are not. They range from the idea that life is far rarer than we think, to the chilling possibility that something systematically wipes out civilizations before they can make contact. Each explanation has its own implications for what our future might hold. Before we dig into those theories, It's worth pausing to appreciate just how strange this problem is. Every time humanity has searched for signals, we've used radio telescopes to scan specific frequencies, optical telescopes to look for laser pulses, and automated surveys to catalog unusual stellar behavior. Our searches have been limited, yes, but the silence has been consistent. Some researchers argue that our search is too narrow, that we're listening for one kind of signal in a universe that might communicate in ways we haven't even imagined. That's a fair point, and it actually makes the problem harder to dismiss. What Fermi realized in 1950, and what keeps scientists up at night today, is that the silence isn't just curious, it's almost mathematically suspicious. The universe had every opportunity to fill itself with minds. Something stopped it. What that something is, and whether it's behind us or still ahead, is the question that changes everything. Because the next theory we're about to explore doesn't just describe the silence. It suggests the silence might be the most important warning humanity has ever received. In 1960, astronomer Frank Drake stood at a chalkboard and wrote an equation that wasn't meant to give answers, but to organize our ignorance. The Drake equation lays out every variable needed to estimate the number of communicating civilizations in our galaxy right now. And when you work through it honestly, it does something unexpected. It shows you exactly where our certainty ends and where the real uncertainty and fear begins. The equation multiplies several factors together. How many stars form in our galaxy each year? How many of those have planets? How many planets are in the habitable zone? How many of those develop life? How many of those develop intelligent life? How many build technology capable of communication? And finally, for how long does that civilization survive and broadcast? The first few variables are now well understood. Astronomers have confirmed that our galaxy produces about 1 to 3 new stars per year. Most of those stars have planetary systems. A significant fraction have planets at the right distance for liquid water. These numbers, confirmed by missions like Kepler, suggest there are hundreds of millions of potentially habitable worlds in our galaxy alone. But then the equation hits a wall. The moment you ask how many habitable planets actually produce life, scientific certainty vanishes. We have exactly one confirmed example of life in the universe, Earth. Every estimate beyond that is just an educated guess. Some scientists believe life emerges almost inevitably wherever conditions allow, because the chemistry is so robust. Others argue that even on Earth, the leap from chemistry to a living cell may have been a near miracle that took hundreds of millions of years, and a lot of luck. That single unknown swings the final answer from millions of civilizations down to just one, us. And we have no way yet to know which estimate is closer to reality, even if we assume that life itself is relatively easy to spark into existence. There's another part of the Drake equation that quietly swallows up all the optimism: the lifespan of a technological civilization. How long does any species, after reaching the point where it can send signals into space, actually survive before it goes silent? If civilizations typically last only a few thousand years after developing radio technology, about where humanity is right now, then the galaxy could be full of brief flashes of intelligence, each one lighting up for a moment, and then fading before another appears. 2 civilizations might each exist for 1,000 years. But if they're separated by millions of years, they'll never overlap. They'll never hear each other. This is called the temporal spacing problem, and it's one of the more quietly unsettling answers to the Fermi Paradox. Not a dramatic extinction, not a cosmic predator, just time, vast and indifferent, keeping every mind in the universe apart. When Frank Drake first ran his equation at a conference in 1960, He estimated there might be about 10 civilizations in our galaxy capable of communication. Modern estimates, depending on how you fill in the unknowns, range from less than 1 to tens of millions. That range tells you everything. We're nowhere close to solving this. We're standing at the edge of the unknown. One of the darkest explanations for why the Drake equation might return such low numbers is something scientists call the Great Filter. The Great Filter isn't a place or a thing you can point to in space. It's a concept first formalized by economist Robin Hanson in 1998, and it might be the most unsettling idea ever put into logical words. The premise is simple: if intelligent life is possible, and the universe is old enough to have produced it countless times, but the galaxy appears empty, then something must be filtering civilizations out before they become widespread. Something is stopping life from reaching the stars. The filter could be a single catastrophic barrier, or it could be a series of smaller hurdles. It might operate at the level of chemistry, making it extremely difficult for life to start in the first place. It could act at the biological level, preventing complex cells from forming. It might be a barrier at the level of intelligence, stopping animals from developing technology. Or it could be a civilizational hurdle, preventing any species from surviving long enough to become interstellar. The truly frightening part isn't just that the filter exists, but the question of where it sits relative to us. If the Great Filter is behind us, then we're incredibly lucky. We've already survived the hardest step, maybe the emergence of life, or the evolution of complex cells, or the leap to intelligence. One of these transitions was so unlikely that almost no other species in the galaxy made it through. We did. If that's true, the road ahead might be open. We could be one of the very few minds in this galaxy, maybe the only one with a real future among the stars. But if the Great Filter is still ahead of us, the implications are much darker. It would mean that every civilization that reaches our level of development eventually hits a wall it can't survive. Nuclear war, environmental collapse, artificial intelligence that escapes control, or some technology we haven't even imagined yet. Something always turns against the species that created it. In this scenario, the silence of the universe isn't a mystery. It's a warning. Every civilization before us tried to cross this threshold and failed. We're approaching it now. There's a way to estimate which scenario is more likely, and the method is deeply unsettling. Finding life elsewhere would normally feel like a triumph, but under the logic of the Great Filter, it could actually be a cause for alarm. If we discover microbial life on Mars, or complex organisms in the oceans of a distant moon, or biosignatures in the atmosphere of an exoplanet, it means the emergence of life is not the filter. Life is common, which means the filter must lie further along the path, closer to us, possibly still ahead. The more life we find in the universe, the worse our odds may become. This is not just speculation, it's a real scientific framing. The Great Filter itself is still theoretical, but no physical law prevents civilizations from spreading. The absence of evidence for any spreading civilization is real, documented, and unexplained. What we do know is this: the silence is real. The math demands an explanation. And whatever is doing the filtering, it's effective enough to have emptied a galaxy. The next question is whether that filter is a product of the universe itself, or something far older and more deliberate. The question of whether the Great Filter is behind or ahead of humanity is one of the most consequential in all of science. Two researchers can look at the same data and reach completely opposite conclusions, both reasonable, one ending in hope, the other in something close to dread. The case for the filter being behind us rests on a series of biological milestones that, in hindsight, look absurdly improbable. The first is the origin of life itself. For hundreds of millions of years after Earth formed, it was a lifeless rock. Life didn't emerge instantly from available chemistry. It took enormous time and, by most estimates, a staggering run of molecular luck. The exact mechanism by which the first self-replicating molecule appeared is still not fully understood. Scientists don't have a complete model for abiogenesis, the process by which chemistry becomes biology. But that may not even be the hardest step. About 2 billion years after simple bacteria appeared, something even stranger happened. One bacterium was absorbed by another cell, and instead of being digested, it became a permanent internal structure. That partnership produced mitochondria, the powerhouse of the cell, and laid the foundation for all multicellular life. It appears to have happened exactly once in 4 billion years of Earth's history. Every plant, animal, and fungus alive today descends from that single improbable merger. If events like these are the filter, then we survived them, and the road ahead might be open. But the case for the filter being ahead is harder to dismiss, and honestly, harder to sit with. Consider the behavioral pattern of every civilization we can observe our own. Humanity reached radio capability about a century ago. In that same 100 years, we developed nuclear weapons, began altering the atmosphere in ways that threaten global stability, and started building artificial intelligence systems whose long-term consequences no one can fully predict. We are, in the language of risk assessment, a species that gains catastrophic power faster than it gains the wisdom to manage it. If this pattern is universal, if every species that reaches technological capability does so before it develops the maturity to handle the consequences, then the filter ahead is not a cosmic accident. It's a developmental trap, a phase every species enters, and most do not leave. There's also a third possibility that doesn't get discussed as openly, but it's just as important. The Great Filter might not be a single, dramatic event. Instead, it could be a series of hurdles, each one thinning the number of civilizations that make it to the next stage. Maybe no single step wipes everyone out, but each barrier reduces the survivors until, by the time a species could be detected across interstellar distances, almost none remain. In this scenario, the galaxy isn't empty because of one catastrophic event, but because the odds are stacked against making it all the way, every step of the journey. This idea fits the data we have. We know we're here, and we know we've survived at least some of the early challenges. But whether the hardest parts are already behind us, or whether we're still approaching the most dangerous threshold any civilization ever faces, is something we simply don't know. What we do know is that the next explanation for the silence in the universe doesn't require destruction at all. It suggests that the conditions for complex life are so rare, Earth might be an extraordinary exception. Back in the late 1990s, paleontologist Peter Ward and astronomer Donald Brownlee introduced a hypothesis that challenged decades of optimism about life in the cosmos. Their argument wasn't that life is impossible elsewhere, but that the emergence of complex, multicellular, intelligent life requires such a precise combination of factors that Earth might be almost unimaginably lucky. This idea became known as the rare Earth hypothesis. Let's break down what makes Earth so unusual. First, there's our location. Earth doesn't orbit just anywhere in the galaxy. It sits in what astronomers call the galactic habitable zone, far enough from the crowded, radiation-filled center to avoid frequent supernovae and gamma-ray bursts, but not so far out that the heavy elements needed for rocky planets are scarce. Stars closer to the center are bombarded by deadly radiation more often, while those on the outskirts lack the chemical richness to build complex worlds. Earth is in a narrow band where conditions have stayed stable for billions of years. Then there's our Sun. It's a stable, middle-aged star that hasn't changed its energy output dramatically over billions of years, giving life time to evolve. Many stars are more volatile or burn out too quickly for complex evolution to take hold. Earth's position in the solar system is also unusual. We have a large moon, whose gravitational pull stabilizes our planet's tilt. Without that, Earth's axis would wobble chaotically, causing wild climate swings that could prevent stable ecosystems from forming. And don't forget Jupiter. The largest planet in our solar system acts as a kind of cosmic shield, its gravity deflecting or absorbing many of the comets and asteroids that might otherwise bombard Earth. More impacts would mean more mass extinctions, and less time for complex life to develop and stabilize. Jupiter's presence may have been crucial. Add to that plate tectonics, which recycle carbon and regulate temperature over millions of years, a magnetic field that protects us from lethal solar radiation, an oxygen-rich atmosphere created by early photosynthetic life, and a temperature range that kept liquid water stable for billions of years. What you get isn't a typical planet. It's a system where dozens of factors lined up just right, one after another. Ward and Brownlee argued that while simple microbial life might be common in the universe, the full stack of conditions needed for complex life is so rare that Earth, like planets capable of producing intelligence, might number in the dozens per galaxy, or even fewer. This idea is still debated. Some scientists push back, saying life is adaptable and could find ways around many of these obstacles. But the rare Earth hypothesis remains one of the most scientifically grounded responses to the Fermi Paradox. It doesn't require a filter or a catastrophe, just that complexity is genuinely hard to achieve. If Ward and Brownlee are right, the silence in the universe has a quiet explanation. It's not that civilizations rise and fall, but that the conditions for intelligence almost never come together in the first place. It's a lonely answer, but not the strangest one on the list. The next hypothesis doesn't suggest that other civilizations failed to form. Instead, it proposes that they formed, thrived, and then made a deliberate decision about us. In 1973, astronomer John Ball introduced an idea that sounds almost comforting, until you think about it for a while. His zoo hypothesis suggests that intelligent civilizations do exist in the galaxy, possibly ancient and highly advanced, and they know we're here. They simply choose not to make contact. The reasoning is similar to how we treat wildlife preserves or isolated human communities. We observe, we study, but we don't interfere, not because we're indifferent, but because we know that uncontrolled contact can destroy what we're trying to observe. If a civilization millions of years older than us decided to monitor Earth, they'd have excellent reasons to stay hidden. History shows that when a technologically superior culture meets a less developed one, the less advanced group is often overwhelmed. Its social structures collapse, its beliefs fracture, and its sense of identity can disintegrate. An alien civilization wise enough to have survived for millions of years would almost certainly understand this dynamic better than we do. Non-interference might not be cruelty. It could be the most ethical response to finding a young, fragile civilization. Under this hypothesis, the silence isn't empty. It's managed. There could be a network of older civilizations that have agreed, formally or by tradition, to leave developing species alone until they reach a certain threshold. That threshold might be a specific level of technology, or a demonstrated ability to cooperate globally, or something we haven't even imagined yet. The zoo hypothesis is, by its nature, extremely hard to test. If a civilization is advanced enough to hide from our instruments, we'd have no way to detect it. Every anomaly we dismiss as natural could, in principle, be managed. The hypothesis survives precisely because it can't be ruled out. But it raises an uncomfortable question. If we're in a zoo, what happens when the exhibit changes? In the last century, humanity has gone from horse-drawn carriages to nuclear weapons, artificial intelligence, and the edge of interstellar communication. If there's a threshold for contact, we may be approaching it faster than anything in our history would suggest. And the question of who decides when we're ready, and what contact actually looks like, is one we have no framework for. Some researchers take the zoo hypothesis a step further, into something a bit darker. Not a preserve maintained out of kindness, but a quarantine maintained out of caution. A civilization that's watched others destabilize their regions of space might isolate emerging civilizations, not for the newcomer's benefit, but for the safety of everyone else. In that version, the silence isn't a gift, it's a fence. The zoo hypothesis, as intriguing as it is, remains just one possible answer to the cosmic silence. There's no confirmed evidence that Earth is being monitored or managed by advanced civilizations. But the absence of evidence isn't the same as evidence of absence, especially when the hypothetical watchers could be millions of years ahead of us in technology and subtlety. What's unsettling is that this idea, for all its strangeness, actually assumes something hopeful. That advanced civilizations can survive long enough to become wise and cautious. But what if wisdom is a luxury that no civilization can afford? That's the premise behind another, much darker theory, the dark forest hypothesis. This idea, popularized by Chinese science fiction author Liu Cixin, is rooted in game theory and survival logic, not just fiction. It starts with two basic assumptions. First, that every civilization's primary instinct is survival, and second, that the universe doesn't have enough resources for unlimited expansion by unlimited civilizations. From these two premises, a chilling conclusion emerges. Imagine you're part of a civilization that detects a signal from another intelligent species. You know nothing about them except that they exist and can broadcast. Now you face a dilemma. You could try to make contact and hope for cooperation, but you can't know their intentions. If they're peaceful and you reach out, you might gain an ally. But if they're hostile and you reveal your location, you could be inviting disaster. If you destroy them preemptively, and they were peaceful, you lose a potential friend. But if they're dangerous and you don't act, you risk your own destruction. The math of this situation, under the assumption of resource scarcity and the impossibility of verifying intentions across interstellar distances, pushes toward a single rational strategy: strike first or stay silent. In the dark forest model, the galaxy isn't quiet because life is rare or fragile. It's quiet because every civilization that survives long enough to understand the stakes chooses to hide. Broadcasting your presence isn't an invitation, it's a risk. Every star is a potential hunter. Every civilization is like a creature moving through a dark forest, making no sound, leaving no trace, hoping nothing notices it. This theory has disturbing implications for us. Humanity has been sending radio waves into space for over a century. Those signals have already traveled more than 100 light years, reaching thousands of star systems. If the dark forest model is correct, we may have already made a dangerous mistake. Some scientists have even argued that we should stop broadcasting altogether. The debate over whether humanity should actively send powerful messages to other stars is real and contentious, precisely because of arguments like this one. Stephen Hawking, before his death, publicly warned against it. The dark forest theory isn't proven science, It's a logical framework built on assumptions about survival and risk. Its weakest point is the idea that cooperation is never worth the risk. Some researchers argue that civilizations advanced enough to be dangerous would also be advanced enough to realize that mutual cooperation offers greater rewards than mutual destruction. But that assumes rationality always scales with technology, and history doesn't always support that. There's also a less sinister version of this idea. Maybe civilizations go quiet not out of aggression, but out of caution. They recognize that contact between species at vastly different levels of development is inherently destabilizing, so they choose silence as the safest path. Either way, the result is the same: a universe that goes dark, not because it's empty, but because everyone is hiding. If you think the dark forest is the most unsettling explanation, the next one is even more sobering. It doesn't require cosmic predators or deliberate hiding. It simply asks us to look at the history of civilizations, ours and others. Every civilization in human history has eventually ended. Empires, cultures, city-states, languages, even entire species, they all rise, flourish, and collapse. This pattern is so consistent that we barely notice it anymore. But when you apply it to the Fermi Paradox, it becomes the loudest signal of all. The self-destruction hypothesis suggests that intelligent civilizations routinely eliminate themselves before they can make meaningful contact with others. Not because of cosmic accidents or alien threats, but through their own inventions and decisions. The timing is what makes this idea so hard to dismiss. Anatomically modern humans have existed for about 250,000 years, but for nearly all of that time, we lived in small, scattered groups with little impact on the planet. Only in the last 12,000 years did we develop agriculture, cities, and organized societies. In just the last few centuries, we built industry. And in the last 100 years, we split the atom, altered the climate, and began building artificial intelligence systems that no one fully understands or controls. The pace of change is the problem. Every century, humanity's capacity for accidental or intentional catastrophe grows faster than our ability to manage it. Today, nuclear arsenals exist that could end complex life on Earth. Engineered pathogens are becoming more accessible as biotechnology advances. Climate disruption is already reshaping the conditions that support civilization. And artificial intelligence is developing along paths that even its creators describe as potentially uncontrollable. These aren't science fiction scenarios, they're real, documented technological realities. The self-destruction hypothesis asks a simple question. If this pattern of accelerating power and lagging wisdom is universal among intelligent species, how many survive the transition from planetary to interstellar capability? If the answer is close to zero, the galaxy fills with brief, brilliant civilizations that burn out before sending a single probe beyond their home system. Researchers sometimes call this the critical phase, the period between a civilization gaining the power to destroy itself and gaining either the wisdom to manage that power or the technology to escape its planet entirely. On Earth, that window opened in the mid-20th century and shows no sign of closing. How long it stays open before something catastrophic happens is a question no one can answer. What makes this especially relevant to the Fermi paradox is scale. Even if 99 out of every 100 civilizations survive their critical phase, the galaxy should still be full of survivors. The silence would remain unexplained. For this hypothesis to fully account for the emptiness, the survival rate would have to be extraordinarily low, maybe close to zero. And that, when you think about it, says something about us right now. We're not observing a failed civilization from the past. We're living inside the critical phase. We are the experiment whose outcome is still undecided. Some researchers see hope in the fact that we're still here, still searching, still asking questions. Others are less optimistic. But the next theory doesn't wait for civilizations to destroy themselves. It suggests something in the galaxy might take a much more active approach. The next explanation for the universe's silence is not a metaphor or a philosophical puzzle. It's a direct, chilling proposition about what a truly advanced civilization might do to ensure its own survival. This is known as the Berserker hypothesis. And once you understand the logic, it's hard to shake from your mind. The idea first appeared in science fiction, but it's been taken seriously by some researchers in astrobiology and existential risk. The scenario goes like this. At some point in the galaxy's history, one or more civilizations reached a level of technology where they could build self-replicating, autonomous machines, probes that could travel through space, make copies of themselves using local materials, and follow a simple directive: destroy any other civilization they find before it becomes a threat. Why would anyone do this? Imagine a civilization that survives for tens of millions of years. Eventually, it faces a problem. If other civilizations are allowed to develop, they might one day become powerful enough to challenge or even destroy the original. From a cold, strategic perspective, the safest move is to eliminate potential rivals before they reach that point. Rather than waiting for a fair fight, you send out machines that can multiply and patrol the galaxy, quietly erasing any sign of technological life they encounter. These berserker probes wouldn't need to be fast or flashy. You only need to build one, as long as it can make copies of itself. Over millions of years, a single probe could become trillions, spreading through the galaxy like a slow, relentless tide. Any planet showing signs of technology would be flagged and, eventually, wiped out. Under this model, the reason the universe is silent is simple: we haven't been found yet, or maybe we have. And the countdown has already started. There's no confirmed evidence of berserker probes. We haven't detected any artifacts or witnessed any destruction events that fit this scenario. But here's the unsettling part. If these machines are designed to be stealthy, we might not recognize them, even if they were here. If they're patient, they might wait until a civilization crosses a certain threshold before acting. We would have no warning. Some scientists have pointed to strange objects like Oumuamua, the mysterious interstellar visitor that passed through our solar system in 2017, as possible candidates for artificial probes. Most astronomers lean toward natural explanations, but the object's odd behavior and shape left the question open longer than usual. The berserker hypothesis also offers a grim explanation for certain patterns in the astronomical record. Some nearby star systems that seemed promising for life show signs of past disruption, though the causes are still debated. What gives the berserker idea its staying power isn't any single piece of evidence, but the logical consistency of the premise. In a universe where survival is a competition and technology can grow without limit, preemptive elimination is a coherent long-term strategy. It's horrifying precisely because it makes sense. The galaxy might not be silent because life is rare or fragile. It might be silent because something already swept through and made it that way. If that's even partly true, the most important question for humanity isn't how to find other civilizations, but whether finding them would be the last thing we ever do. But not every theory about the Fermi Paradox is so grim. Some explanations don't involve destruction at all, but instead focus on timing and speed. In 2020, a group of astrophysicists, including Robin Hanson, proposed a model that reframes the paradox in a way that cuts through much of the speculation. They called it the grabby aliens model. This framework starts with a simple assumption. When civilizations reach a certain level of technology, they expand rapidly and permanently. The model doesn't assume hostility or self-replicating machines. It just assumes that a technologically advanced civilization, given enough time, will spread outward through space at a significant fraction of the speed of light, colonizing star systems and leaving behind a visible, expanding bubble of altered space. Here's the key insight. If such civilizations existed and started expanding even 1 billion years ago, their bubbles would already have reached us. The galaxy is old enough, and the physics of expansion is fast enough, that any civilization with a significant head start would have made contact by now, not necessarily through radio signals, but by physically arriving. The fact that we haven't been absorbed, contacted, or even brushed by the edge of any such expanding civilization is itself significant data. According to the Grabby aliens model, this means one of two things: either there are no such civilizations, because something prevents them from reaching the expansion phase, or they exist but haven't started yet. In other words, we might be living at the very beginning of the era when the first, Grabby, civilizations are about to emerge, and we could be one of them. This possibility carries a striking implication. If Grabby civilizations are rare but inevitable, and if we're close in cosmic time to when the first ones appear, then humanity may be among the very first species to reach this threshold. We're not late to the party, we're early, extremely early. The model predicts that if you looked at the universe in 1 billion years, you'd see it filling up with competing spheres of influence from multiple originating civilizations, each growing outward at a fraction of light speed, eventually meeting at boundaries and establishing some kind of equilibrium or conflict. Right now, the universe looks empty because the expansion age hasn't started yet. The window of silence we observe may be temporary, a cosmic dawn before a very noisy day. The Grabby aliens model has been peer-reviewed and taken seriously in academic circles. It doesn't resolve every edge of the Fermi Paradox, but it offers a mathematically coherent answer to the timing question. We see no expanding civilizations because the expansion age is only just beginning. Whether this is reassuring or alarming depends on your perspective. On one hand, we may simply be first, not alone in a dangerous universe, but pioneers. On the other hand, if we're among the first Grabby civilizations to emerge, then the choices we make in this century about how we expand, what we consume, and how we treat the life we encounter will set a precedent that echoes across billions of years of cosmic history. That's not a small responsibility. But not everyone thinks the answer to the Fermi Paradox is written in the stars. Some believe it might be written in the very code of reality itself. The next theory is arguably the strangest yet. The next explanation for the Fermi Paradox doesn't come from astronomy or biology, but from philosophy and computer science. It's called the simulation hypothesis, and it was formalized by philosopher Nick Bostrom in 2003. This idea doesn't claim we are definitely living in a simulation, but it lays out a logical trilemma. Either almost all civilizations at our stage of development go extinct before they become capable of running detailed simulations of conscious beings, or almost all advanced civilizations choose not to run such simulations, or we are almost certainly living inside a simulation right now. The reasoning is surprisingly straightforward. If even one civilization in the history of the universe survives long enough and decides to run detailed simulations of minds, it could create an astronomical number of simulated realities. The simulated minds would vastly outnumber the real ones. Statistically, then, any randomly selected conscious being, including you, would be far more likely to be simulated than real. So, what does this have to do with the Fermi Paradox? If we are inside a simulation, the silence of the universe is easily explained. The sky is empty, because the creators of the simulation didn't bother to populate it with other civilizations. There are no signals, no visitors, no artifacts, because the simulation only renders what its designers want us to see. Beyond the reach of our telescopes, there may be nothing at all, not empty space, but simply the absence of code. This isn't a scientific hypothesis in the traditional sense, because it's not currently testable. But it's not pure fantasy, either. Some physicists have proposed experiments that might detect signs of a discretized, pixelated, space-time, the kind of artifact you'd expect if reality were built on a computational grid rather than continuous mathematics. So far, no definitive evidence has emerged, but the question remains open. From the perspective of the Fermi Paradox, the simulation argument is both the simplest and the strangest answer. It doesn't require a great filter, self-destruction, or alien predators. It just requires us to accept the possibility that there's a layer of reality above the one we can observe, and that whoever operates that layer chose not to include other voices in our version of the cosmos. Some scientists push back, arguing that simulating a universe with the detail we observe would require impossible amounts of computing power. But we don't know the limits of computation for an entity outside our own physics. What makes this theory compelling in the context of Fermi is its explanatory power. The silence isn't a puzzle to solve, it's a design choice. And if it's a design choice, the question shifts from, where is everybody? To, why were we made to feel alone? That's a question science can't answer, at least, not yet. But it's a possibility that makes the silence feel intentional, curated, and perhaps even meaningful. Whether that's comforting or disturbing depends on your perspective. Let's leave philosophy for a moment and return to biology, because the next explanation is grounded in hard science and may be the most sobering of all. For much of the 20th century, scientists assumed that once life began, it would naturally become more complex over time. Simple organisms would evolve into multicellular ones, which would develop nervous systems, then brains, and eventually intelligence. Earth was just one of countless planets riding this evolutionary escalator. But over the past 2 decades, that assumption has quietly unraveled, not because of a single dramatic discovery, but because of the growing realization of just how fragile and contingent the path from simple to complex life actually was on Earth. Let's look at the timeline. Life appeared on Earth within a few 100 million years after the planet formed, a relatively quick start, suggesting that the origin of simple life might not be the main barrier. But then, for nearly 3 billion years, single-celled organisms dominated the planet. 3 billion years of evolution, chemistry, and environmental change, and life went nowhere structurally complex. Then, at some point, a new kind of cell appeared, the eukaryote. This cell type, which forms the basis of all plants, animals, and fungi, arose from a single, rare event, a merger between 2 different organisms, where one cell absorbed another and kept it as an internal energy source. This produced mitochondria, the powerhouse of the cell. Scientists believe this happened exactly once in Earth's history. After eukaryotes appeared, another billion years passed before multicellular life became common. Then, in a geologically brief period known as the Cambrian explosion, most major animal body plans appeared, possibly triggered by a rise in atmospheric oxygen. Each of these transitions required a specific set of preconditions: the right chemistry, a stable environment, and a lucky mutation at just the right time. Miss any one of these, and you get a planet of bacteria forever. Harvard researcher Andrew Knoll has spent decades studying early Earth life, and argues that the emergence of complexity was neither inevitable nor predictable. It was a series of accidents, each one necessary for the next. From a scientific standpoint, this isn't pessimism. It's an honest reading of the fossil and molecular record. If this analysis is correct, then the universe probably isn't empty of life. It's probably full of bacteria and simple organisms, thriving in oceans beneath ice shells or in warm rocks on thousands of worlds. But the leap to complexity, to nervous systems, brains, language, and technology, may have happened only a handful of times in the entire observable universe. Simple life is likely common. Complex life may be the rarest thing in existence. If that's true, the silence of the sky isn't because the universe is dead. It's because complexity is a nearly impossible accident that happened to us and almost nowhere else. And if that's the case, the stakes for our own survival just got much higher. Because what comes next is the possibility that not only is complex life rare, but that intelligent, technological life may have happened exactly once, here, on Earth. There's a version of the Fermi solution that doesn't require catastrophe, filters, alien hunters, or simulations. It just combines probability with the known age and structure of the universe, and concludes: we may be the first intelligent civilization to ever exist anywhere. The idea that we might be the very first intelligent civilization in the universe doesn't come from arrogance. It comes from timing. The universe is about 13.8 billion years old, but for the first 9 billion years or so, the conditions for complex, rocky planets like Earth weren't really in place. The earliest stars were made almost entirely of hydrogen and helium. They burned hot and fast, then exploded, seeding the cosmos with heavier elements like carbon, oxygen, and iron, ingredients essential for chemistry and biology as we know them. It took several generations of stars living and dying before enough of these elements accumulated to build planets like ours. Earth itself formed about 4.5 billion years ago. Life appeared relatively quickly, but complex life took over 3 billion years to emerge. And technological intelligence took hundreds of millions more. When you plot humanity's appearance on the timeline of cosmic chemical enrichment, we show up almost as soon as it's physically possible for beings like us to exist, not billions of years late to a crowded party, but right at the beginning. If the emergence of intelligence requires a certain richness of heavy elements, which only became widespread in the last 5 to 8 billion years, and if it also requires billions of years of biological evolution, then there's a narrow window at the front edge of possibility where the first minds could appear. We may be sitting in that window right now. Under this framing, the universe isn't old enough to be full of intelligence yet. We're not survivors of a galactic apocalypse, nor are we being ignored by ancient, wise civilizations. We're simply early, the first, or among the very first, to cross the threshold into technological awareness. The implications are staggering. If we are first, everything that happens next is a blank page. There's no elder civilization to learn from, no template to follow, no warnings from predecessors who already made the mistakes. We are making the first footprints in what could eventually become a universe full of intelligence, but only if we survive long enough to pass something forward. This isn't just idle speculation. Researchers like David Kipping at Columbia University have published work suggesting that, based on the distribution of times when intelligence could emerge, it's actually likely that the first civilizations would appear early, not late. The loneliness of this hypothesis is different from others. It's not the loneliness of the last survivor, but the loneliness of the first arrival, a universe full of potential, none of it yet realized, and us standing at the beginning of something that has never happened before. If we are first, The survival of our civilization isn't just our concern. It's the only thread connecting the universe to the possibility of a future full of minds. And if that's not enough to make you pause, the next chapter suggests that maybe the problem isn't with the universe at all, but with the way we're searching. For decades, the search for extraterrestrial intelligence, SETI, has focused on one main method: listening for radio signals. Since Project Ozma in 1960, astronomers have pointed radio telescopes at the sky, hoping to catch a structured signal that couldn't be produced by natural processes. It's a reasonable approach, and it's scientifically sound, but it might be missing the point entirely. Here's the issue. Radio waves spread out as they travel, their energy dispersing over an ever-growing sphere. By the time a signal has traveled even a few hundred light years, it's so diluted that it's almost impossible to distinguish from the background noise of the universe. Even our most powerful intentional broadcasts, like the Arecibo message sent in 1974, would be undetectable to current human technology at even a fraction of the distance to the nearest stars. This means that even if hundreds of civilizations were broadcasting with technology similar to ours, we almost certainly wouldn't detect them from interstellar distances. Radio just isn't a good medium for interstellar communication at our level of development, and civilizations more advanced than us may have stopped using it long ago. Think about our own trajectory. We've been broadcasting strong, omnidirectional radio signals for about a century. But communication technology is already moving away from high-powered, broad transmissions toward tightly focused, encrypted digital signals. Fiber optics and direct links are replacing radio towers. As a civilization's communication infrastructure matures, it becomes quieter and harder to detect from the outside. An advanced civilization might be effectively invisible to radio-based searches, not because it stopped communicating, but because it switched to methods we haven't even invented yet. Laser pulses, neutrino signals, gravitational wave modulation. Any of these could pass through our instruments without leaving a recognizable trace. That's why researchers are increasingly advocating for a shift towards searching for technosignatures, evidence of technology that persists and scales beyond what individual broadcasts can offer. This could include heat signatures from industrialized planets, atmospheric chemistry that doesn't match any natural model, or structured light curves from stars with engineered objects in orbit. These markers would be much harder to hide and wouldn't require a civilization to be actively trying to communicate. The logic is simple. If you want to find a city, you don't listen for phone calls, you look for lights from above. Our current search strategy is like listening for phone calls across an ocean, while the city we're looking for stopped using phones a century ago. The silence we hear may have nothing to do with absence. It may have everything to do with the limits of our instruments and the assumptions built into our methods. This is not a fringe argument. It's central to the current direction of astrobiology research and is increasingly influencing how funding bodies prioritize searches. And speaking of things we may have already seen but not recognized, the next chapter concerns one of the most famous anomalies in the history of this entire search. A signal that appeared once, lasted just over a minute, and has never been explained. If a civilization advanced enough to build structures visible from across the galaxy exists, it almost certainly wouldn't announce itself with a radio broadcast. It would announce itself by reshaping its environment on a scale so enormous that the evidence would be embedded in the light of distant stars, detectable by any civilization patient enough to look. This is the logic behind the search for technosignatures. The hunt for physical evidence of technology, rather than intentional communication. And the most iconic object in that search is the Dyson sphere. The concept of the Dyson sphere was first introduced by physicist Freeman Dyson in 1960. He proposed that any civilization facing energy limitations would eventually realize the most obvious solution: harnessing the full output of its star. This wouldn't necessarily mean building a solid shell around the star. More likely, it would involve a vast swarm of orbiting collectors, habitats, or satellites, all working together to capture as much stellar energy as possible. From a distance, a star surrounded by such a structure would look very strange. It would emit less visible light than expected for its size and type, while radiating an unusual amount of energy in the infrared spectrum. That's because the collectors would absorb the star's light and re-emit waste heat as infrared radiation. This specific signature, dimmer visible light combined with excess infrared, can be detected by our instruments across thousands of light years. Astronomers have actually cataloged stars that behave in odd ways, and some have been flagged as possible Dyson sphere candidates. None have been confirmed as artificial, but the search has only recently become systematic. Missions like Gaia, the Wide Field Infrared Survey Explorer, and the upcoming Nancy Grace Roman Space Telescope are generating massive catalogs of stellar behavior, making it possible to search for these technosignatures at a scale never before attempted. For the first time, researchers are using machine learning to sift through this data, looking for stars that don't fit any known natural model, stars that dim in irregular, structured patterns, or radiate more heat than they should. Beyond Dyson spheres, scientists are also searching for other signs of large-scale engineering stars losing mass in unusual ways. Planetary systems with odd orbital arrangements, or gas giants that appear to have been stripped of their outer layers. None of these have been confirmed as evidence of alien technology, but the scientific community now takes technosignature research seriously. In fact, NASA began formally funding this kind of work in 2019, marking a major shift in institutional attitude. One particular class of technosignature has generated enormous interest: stars whose light dims in irregular, non-repeating ways. Not the predictable dips caused by orbiting planets, but complex fluctuations that vary in depth, duration, and shape. This is not what any known natural object consistently produces, and it's been observed in a real star system. That star, located about 1/500 light-years away, has become one of the most studied and debated objects in modern astronomy. Its behavior has sparked more peer-reviewed papers, more competing theories, and more genuine scientific controversy than almost any other single star in recent memory. What's happening around that star, and why scientists still can't fully agree on a natural explanation, is a story that highlights just how much we still have to learn. But before we get to that, let's revisit one of the most famous anomalies in the history of the search for extraterrestrial intelligence, a signal that, for a brief moment, seemed to offer a tantalizing hint that we might not be alone. On August 15, 1977, a radio telescope at Ohio State University, part of a project called Big Ear, detected something extraordinary. The telescope was scanning the sky automatically, recording columns of data on long sheets of paper. Days later, a volunteer named Jerry Emmon was reviewing the printouts when he noticed a sequence of numbers and letters that stood out from everything else. The signal lasted exactly 72 seconds, the maximum time the telescope could observe any given point in the sky. It appeared to come from the direction of the constellation Sagittarius. It had the intensity, frequency, and narrow band structure that researchers had predicted an artificial extraterrestrial signal might have. Emmon circled the data and wrote a single word in the margin: "Wow." The "wow" signal has never been detected again. Dozens of follow-up observations have targeted the same region of sky, using more powerful instruments, but nothing has ever reappeared. No repetition, no faint echo, no corroborating detection from any other telescope. Whatever produced it either appeared once, moved on, or stopped. The signal is real, and its characteristics are genuinely unusual. Over the decades, scientists have proposed various natural explanations. One recent idea suggested a comet releasing hydrogen gas in just the right direction. But further analysis showed that the comets in question weren't in the right place at the right time, and the hydrogen explanation didn't fit the signal's narrow band nature. The wow signal remains in a rare scientific category, an anomaly with no confirmed natural explanation, but also no confirmed artificial one. It's not proof of extraterrestrial intelligence, but it's a data point that science can't yet explain. What makes the wow signal especially intriguing is the frequency. It appeared near 420 MHz, the emission frequency of neutral hydrogen, the most common element in the universe. Decades before the signal was detected, researchers had suggested that this frequency would be a logical choice for any civilization trying to make contact, a universal radio landmark that any species studying the cosmos would recognize. The wow signal appeared exactly there. Whether that's an extraordinary coincidence or something more meaningful, we still don't know. Nearly 50 years of follow-up observations have failed to produce a satisfying natural explanation. That absence isn't evidence of an alien origin, but it is evidence that we encountered something our models haven't fully accounted for. One observation, one margin note, and decades of silence from the same patch of sky. If the wow signal was the most famous single anomaly of the last century, the next one arrived more recently, lasted for years instead of seconds, and produced a level of scientific confusion that the field hadn't seen in decades. In 2015, astronomer Tabetha Boyajian and her team published a paper describing a star about 400 light-years away that was behaving in a way no natural model could easily explain. Catalogued as KIC 84628522, but now widely known as Tabby's star, it was dimming, not in the regular, predictable way caused by an orbiting planet, but in complex, irregular bursts. Sometimes it would dim by as much as 22% over a few days, then brighten, then dim again in a completely different pattern. A Jupiter-sized planet blocks about 1% of a star's light. Whatever was blocking Tabby's star was, by natural standards, impossibly large, and the pattern wasn't regular, symmetric, or consistent with any known orbiting body. The data on Tabby's star came from the Kepler Space Telescope, which monitored over 150,000 stars for planetary transits. Out of all those stars, Tabby's star produced the most bizarre and perplexing light curve in the entire dataset. Citizen scientists working with the Planet Hunters project were the first to flag it as something truly unusual, and their instincts were right. The star's dimming events were not only deep, sometimes blocking more than a fifth of the star's light, but also irregular, unpredictable, and without any clear periodicity. Naturally, the first explanations considered were the most dramatic. The irregular dimming pattern was exactly the kind of thing you might expect from a swarm of artificial structures. Perhaps a Dyson swarm in the process of being built, with large objects of varying sizes and shapes orbiting the star and blocking its light in complex ways. This wasn't just wild speculation. The idea was raised in peer-reviewed journals and taken seriously by a number of researchers. After all, if you were looking for evidence of alien engineering, this is the sort of anomaly you'd hope to find. But science is cautious, and the community didn't settle on the alien megastructure hypothesis. After years of intense observation and debate, The most widely accepted explanation is that a cloud of disintegrating dust and debris, possibly from a shattered family of comets or a disrupted belt of rocky bodies, is responsible for the strange dimming. However, even this natural explanation has its own unresolved issues. The sheer scale and complexity of the dimming events are difficult to fully account for with current models. More recently, astronomers have noticed that Tabby's star also shows a slow, long-term fading trend, separate from the sharp dips, adding yet another layer of mystery. Tabitha Boyajian herself has always been careful in her public statements, emphasizing that the most likely explanation is natural, and that no evidence of artificial construction has been confirmed. That's the right approach for science. But she's also acknowledged that the object remains unexplained, and that's what keeps the scientific community interested. What makes Tabby's star so significant in the context of the Fermi Paradox isn't just the possibility of alien technology. It's what the object represents for the scientific method. For the first time, astronomers found a real star system exhibiting behavior that, without any bias toward dramatic conclusions, would be flagged as a candidate for serious investigation by anyone searching for technosignatures. The instruments worked. The anomaly was real. The natural explanations remain incomplete. That's not proof of alien engineering. But it's a demonstration that searching for technosignatures might actually work, and that we're only just beginning to understand what's possible. If Tabby's star left researchers unsettled, the next cosmic anomaly was even stranger. It didn't sit quietly in a distant system, dimming and brightening. Instead, it traveled through our own solar system, behaving in ways that defied every expectation. In October 2017, astronomers at the Halakal Observatory in Hawaii detected a fast, moving object passing through the solar system. At first, it was thought to be a comet from our own neighborhood. But further analysis revealed something unprecedented. The object had come from outside the solar system entirely. It was the first confirmed interstellar visitor ever detected. They named it Oumuamua, a Hawaiian word meaning, a messenger from afar arriving first. Initially, astronomers expected Oumuamua to be a straightforward case, a chunk of rock or ice ejected from another star system, drifting through space for millions of years before a chance encounter brought it near the sun. The universe is old, and ejected debris should be common. But as more data came in, the story became anything but simple. Oumuamua's shape was unlike anything previously observed, based on its brightness and how it reflected sunlight. It appeared to be extremely elongated, perhaps 10 times longer than it was wide, like a cosmic cigar, or even a flat pancake. No known natural process reliably produces objects with that geometry at that scale. Comets and asteroids are irregular, but not to this extreme. Then came the real puzzle. As Oumuamua moved away from the sun, it accelerated, just a little, but enough to be measured. Comets do this when sunlight vaporizes their ices, creating jets that push them along. But astronomers saw no evidence of outgassing, no visible tail, no dust, nothing. Every natural explanation for the acceleration was tested and found wanting. Some suggested it was made of hydrogen ice, which would sublimate invisibly. But hydrogen ice isn't stable in interstellar space for long enough to survive the journey. Others proposed it was a thin, flat shard of natural material pushed by sunlight, but such a geometry is not known to form naturally. Avi Loeb, a Harvard astrophysicist, publicly argued that the simplest explanation for all of Oumuamua's properties, taken together, was that it might be artificial. Not that it definitely was, but that the hypothesis deserved serious scientific consideration. Most of the scientific community disagreed, expecting that a natural explanation would eventually emerge. In 2023, A new theory suggested Oumuamua could be a fragment of nitrogen ice from a shattered exoplanet, but this idea, too, has not been universally accepted. What Oumuamua confirmed, regardless of its true nature, is that interstellar objects do pass through our solar system, and that at least one of them behaved in ways our models did not predict. A second interstellar object, Borisov, arrived in 2019 and behaved exactly like a typical comet, which only deepened the mystery of the first. The story of Oumuamua isn't closed. The object is now far beyond the reach of any telescope, and whatever secrets it carried are gone with it. But its brief visit forced astronomers to confront the possibility that things from outside our solar system can arrive without warning and leave without explanation. It raises a sobering question: what else might be out there that we're not equipped to recognize? One of the quieter explanations for the Fermi Paradox doesn't require aliens to be rare, destroyed, or hiding. It simply suggests that the universe is structured in a way that makes traveling across it fundamentally difficult for any civilization, no matter how advanced. And the more closely you look at the physics, the harder it is to dismiss this idea. The idea that the universe itself might be the ultimate barrier to interstellar contact is both simple and profound. The first and most obvious obstacle is energy. To accelerate a spacecraft to even a tenth of the speed of light, a minimum for practical interstellar travel within a human lifetime, requires an amount of energy that dwarfs anything our civilization has ever produced. For a modestly sized probe, the energy needed is equivalent to detonating thousands of nuclear bombs. If you scale up to a ship carrying life support, shielding, and supplies, the requirements become almost unimaginable. Then there's the fuel paradox. Any rocket must carry its own fuel. But fuel has mass, and the more mass you add, the more fuel you need to move it. This relationship is exponential, not linear. As the distance increases, the amount of fuel required quickly becomes absurd. Chemical rockets are obviously inadequate. Even nuclear propulsion, while a huge improvement, doesn't solve the problem. Fusion drives, if we ever develop them, would help. But even then, the engineering challenges for a true interstellar mission are centuries beyond our current capabilities. Time is the next barrier. Even at a tenth of light speed, the closest star system, Proxima Centauri, is over 40 years away. The nearest potentially habitable planets are even farther. To explore the entire galaxy, which is about 100,000 light years across, would take millions of years, even for unmanned probes. Any civilization attempting such a project would need to maintain stability and purpose over timescales that dwarf all of human history. And then there's the risk of collisions. Interstellar space isn't empty. Tiny grains of dust and small rocks, invisible from afar, become deadly at high speeds. A particle no bigger than a grain of sand, if struck at a significant fraction of light speed, would release energy equivalent to a small bomb. Shielding a spacecraft against such impacts for decades or centuries of travel is a problem we don't know how to solve. These barriers are not just engineering challenges. They are dictated by the laws of physics as we understand them. They don't disappear with optimism or clever ideas. What they suggest is that even the most advanced civilizations might conclude that physical interstellar travel simply isn't worth the cost or risk. The galaxy could be full of intelligent species who have never left their home systems, not because they lack curiosity, but because the universe itself keeps them confined. If that's true, the silence we observe isn't a sign of absence, but a sign of isolation. Each civilization is locked in its own small bubble of space, perhaps listening, perhaps transmitting, but unable to bridge the vast distances that separate them. And if that's the case, the next question is even stranger. Could a civilization still leave a detectable mark without ever traveling? And are there any such marks that we've already missed? Most discussions of the Fermi Paradox focus on space. Where are they? Why haven't they come here? But there's another version of the problem that operates entirely in time, and it may be even more unsettling. The universe is 13.8 billion years old. Complex life on Earth took about 4 billion years to evolve intelligence. If the conditions for intelligence existed elsewhere in the galaxy billions of years before Earth, then it's possible that civilizations rose, flourished, and vanished long before humans ever appeared. A civilization that peaked 2 billion years ago would leave no radio signals for us to detect today. Their broadcasts, if they ever reached our part of the galaxy, would have passed by when Earth was still a world of single-celled organisms. Any physical artifacts they launched into space would, after billions of years, be indistinguishable from natural debris, battered and scattered by cosmic processes. The same is true in reverse. Civilizations that will emerge millions or billions of years from now will arrive long after we're gone. From their perspective, we will be the ancient silent ones. Our signals will have faded, our artifacts, if any survive, will be incomprehensible relics. This is sometimes called the temporal communication problem. Two civilizations can share the same galaxy, and yet be so separated in time that they never have a chance to sense each other's existence. The overlap required for detection isn't just about being close in space. It's about being close in time, and on cosmic scales, that window is incredibly narrow. Astronomer Milan Urkovic has written extensively about this idea, arguing that our search for extraterrestrial intelligence is built on the assumption that civilizations exist on timescales similar to ours. But if civilizations can last millions or billions of years, the galaxy's history of intelligence might be mostly in its past, not its present. We might be searching for something that flourished and faded long before our instruments existed. There's also a forward-looking version of this argument. If intelligence is genuinely rare, and we are among the first, then the full flowering of minds in this universe may lie tens or hundreds of millions of years in the future. We're not late arrivals to an empty party, we're the very early ones, and the party itself has barely started. Whether that's hopeful or isolating probably depends on your mood. This perspective shifts the question from, where is everybody? To, when is everybody? And in doing so, it removes some of the urgency from the silence. The galaxy may not be empty, it may simply be early. But there's another class of civilizations that might exist right now, in this very moment, that no telescope can find. Not because they're hiding, not because they're destroyed, but because they never developed any technology we would recognize as a signal at all. There's an assumption so deeply embedded in the search for extraterrestrial intelligence that it almost never gets questioned. The idea that intelligence leads to technology. That any species capable of abstract reasoning will eventually build machines, generate electromagnetic signals, and leave a detectable mark on its environment. Earth's history supports this, but Earth is only one example. Consider the cognitive sophistication of some Earth species that never developed technology. Dolphins recognize themselves in mirrors, have complex social structures, and use regional dialects. Elephants grieve their dead and remember individuals for decades. Crows and ravens make tools, plan for the future, and recognize human faces. Octopuses solve puzzles and learn by observation, despite having a nervous system completely different from ours. None of these species are building radio transmitters. Intelligence and technological civilization are not the same thing. Intelligence is a cognitive trait, technological civilization is a specific path that depends on a unique combination of biology, environment, and culture. Remove any one of those factors, and you might have a planet full of intelligent beings who live rich, complex lives, while leaving no trace detectable from space. This possibility, that intelligence doesn't always lead to technology, scales up in a way that's both humbling and unsettling. Imagine a world covered in oceans, teeming with intelligent marine life. These beings might have language, culture, and even philosophy. But without hands or fire, they'd never develop electronics or metalworking. Their entire civilization could be rich and ancient, yet from space, their planet would look like a featureless blue marble. Multiply this scenario by thousands of worlds, and suddenly the universe could be full of minds, none of which ever send a signal we could detect. Astrobiologists are starting to take this idea seriously. Some now argue that the definition of intelligence used in the search for extraterrestrial life is too narrow. We're not really searching for intelligence, we're searching for industrial civilization. And there's no guarantee that intelligence and industry always go hand in hand. This doesn't fully solve the Fermi Paradox, of course. Even if most intelligent species never build technology, it only takes one to light up the galaxy. But it does add another layer to the silence. Some of what we're not hearing may not be silence at all, but a conversation in a language or medium we can't even imagine. And the next layer goes deeper still. Even among species that do develop technology, the very structure of their minds might make it impossible for us to recognize what they're building or saying. Our search for extraterrestrial intelligence is built on the assumption that alien minds will think enough like us that we'll recognize their signals, structured sequences, mathematical patterns, geometric artifacts. But that assumption has never been tested against anything but human intelligence. Consider what a truly alien intelligence might be like. Not just a different language or culture, but a mind shaped by entirely different evolutionary pressures, senses, and social structures. Maybe they process information in parallel streams instead of a single thread. Maybe their memories are distributed across a colony, or their communication is chemical, not electromagnetic. There's no guarantee that such an intelligence would produce anything we'd recognize as a signal. Their artifacts might look like natural noise to us. Their technology might operate on principles we understand in theory but have never seen applied. Even on Earth, researchers studying animal cognition have run into smaller versions of this problem. For decades, animal communication was judged by how much it resembled human language. Species that didn't fit that mold were dismissed as non-linguistic. But as scientists developed new frameworks, they discovered surprising complexity. Prairie dogs have calls that describe predators in detail. Whale songs have mathematical structure. Bees communicate direction and distance through dance. These are animals that share billions of years of evolutionary history with us. Imagine the gap with a species that shares none. The tools we use to search for signals are tuned to patterns our minds can process. Patterns outside that range will pass through our instruments unnoticed. The Fermi Paradox might not be about where everyone is. It might be about whether we could even recognize them if they were right in front of us. The silence could be a communication breakdown at the deepest level, not a failure to transmit, but a failure to perceive. And if that cognitive barrier applies to what we can receive, it applies equally to what we can send. Every message we broadcast is built for human minds. Whether it would mean anything to a radically different intelligence is a question we can't answer from inside our own perspective. This leads to one of the most provocative ideas in the field. Maybe alien intelligence has already arrived here, and we simply haven't recognized it. In 1973, Francis Crick, the co-discoverer of DNA's structure, and astronomer Leslie Orgel proposed a hypothesis called directed panspermia. They suggested that life on Earth might not have originated here at all, but was deliberately seeded by an extraterrestrial civilization. Crick wasn't motivated by science fiction, but by the sheer improbability of life's rapid appearance on early Earth. Life showed up almost as soon as the planet cooled enough to support it, and the genetic code is astonishingly universal. Every known organism uses the same basic system for translating DNA into proteins. Crick found this suspicious. It suggested either a single common origin or a deliberate design. Directed panspermia proposes that a civilization facing extinction, or simply wishing to spread life, might send microbial life, or the building blocks of biology, to promising worlds across the galaxy, not to colonize, but to ensure that life would take root wherever conditions allowed. If this is true, the Fermi Paradox changes shape. The origin of life on Earth wouldn't be an independent event, but evidence of a prior civilization that may no longer exist, or that exists in a form we can't recognize. This idea is almost impossible to prove or disprove. The universality of the genetic code can be explained by common descent, and the speed of life's appearance on Earth, while surprising, has plausible natural explanations. But the hypothesis does force us to ask different questions about the search for life. If panspermia, directed or natural, is real, then finding life elsewhere in the galaxy wouldn't necessarily mean an independent origin. Two worlds with life might share a common ancestor, either through natural transfer of material or deliberate seeding. Recent research supports at least the natural version of this idea. Rocks ejected from planetary surfaces during impacts can travel between star systems over millions of years, potentially carrying dormant microbes. If those rocks land on a suitable world, life could spread without any civilization's involvement. The directed version simply adds intent to a process that might already happen naturally. Whether or not any civilization deliberately seeded the galaxy, the question of our own origins is less settled than it might seem. The precise mechanism by which chemistry became biology on Earth is still an open question. Crick's hypothesis sits at the edge of that mystery. And if we were placed here intentionally, the civilization that did so might have left more than just life. They might have left a message. Some researchers have begun to wonder if the answer to the Fermi Paradox might not require a telescope at all. Maybe it's hidden somewhere much closer, perhaps even within our own DNA. The idea that the answer to the Fermi Paradox could be hidden within us, within our very biology, has gained traction in recent years. Some scientists have speculated that if life on Earth was seeded intentionally, the architects might have left a message embedded in the genetic code itself. DNA is an incredibly dense and stable information storage medium. In theory, a sufficiently advanced civilization could encode a message in the non-coding regions of DNA, the so-called junk DNA that makes up the vast majority of our genome. Such a message could persist for billions of years, passed down through every living thing on the planet. Physicist Paul Davies has written about this possibility, calling it a cosmic legacy. He suggests that if we ever find a mathematically structured pattern or an artificial sequence in our DNA that cannot be explained by natural evolution, it could be evidence of intentional design, a kind of biological time capsule from another world. So far, no such message has been found, but the search is still in its infancy. The human genome is vast, and most of it remains poorly understood. The idea is speculative, but it's not outside the realm of scientific curiosity. There's also a simpler version of this idea. If life on Earth was seeded from elsewhere, whether intentionally or by natural panspermia, then our biology itself is evidence of life's presence beyond our planet. Every cell in our bodies could carry the chemical signature of an origin that began somewhere else in the galaxy. In this sense, the answer to the Fermi Paradox might have been inside us all along, not in our technology or our telescopes, but in the molecules that make us who we are. But if the answer isn't hidden in our DNA, maybe it's hidden in the very structure of the universe we observe. Philosopher Stephen Webb proposed the planetarium hypothesis, which suggests that the cosmos we see is a kind of managed illusion. According to this idea, a sufficiently advanced civilization could manipulate the electromagnetic signals reaching our solar system, creating the appearance of an empty universe. We would have no way of knowing if the stars and galaxies we observe are real or simply projections, carefully curated to keep us isolated. This hypothesis is, by its nature, untestable. If the illusion is perfect, we would never detect the deception. It's less a scientific theory than a philosophical boundary, a reminder that our knowledge of the universe is limited by what we can observe, and that our observations could, in principle, be manipulated by forces beyond our comprehension. The planetarium hypothesis is a more elaborate version of the zoo hypothesis, but instead of passive observation, it involves active management of our cosmic perspective. There's a less conspiratorial version of this idea as well. The observable universe is simply too small a sample to contain evidence of other civilizations. The universe may be vastly larger than what we can see, and other civilizations may exist so far away that their light hasn't had time to reach us since they formed. In this view, the silence we observe is not the silence of the universe, but the silence of our tiny corner of it. Regardless of whether the silence is managed or accidental, the fact remains that we are working with incomplete information, and that incompleteness may be the most haunting aspect of the Fermi Paradox. Are we alone because the universe is empty, or because we're looking in the wrong way, at the wrong time, or with the wrong tools? Meanwhile, the search for life beyond Earth is entering a new era. For decades, astrobiology was a field of theory and speculation, with little observational data to guide it. But that's changing rapidly. The James Webb Space Telescope, launched in 2021, has given astronomers the ability to analyze the atmospheres of exoplanets with unprecedented precision. When a planet passes in front of its star, a tiny fraction of starlight filters through its atmosphere before reaching us. By analyzing which wavelengths are absorbed, scientists can identify the chemical composition of that atmosphere. Even from hundreds of light years away in 2023, researchers using the James Webb Telescope announced the detection of carbon dioxide and sulfur dioxide in the atmosphere of a planet called K2-18b, a world about 2.5 times the size of Earth, orbiting in the habitable zone of a cool star. Sulfur dioxide can be produced by photochemical reactions involving biological molecules in ocean water under certain conditions. The finding was described as tentative, but it was a proof of concept. We now have the tools to detect biologically relevant chemistry on distant worlds. Then, in 2025, the same team reported evidence of dimethyl sulfide in the atmosphere of K2-18b. On Earth, this molecule is produced almost exclusively by marine phytoplankton. There is no known abiotic process that generates it in the concentrations observed. The signal was statistically significant, but not yet at the level required for a confirmed discovery. The scientific community responded with both excitement and caution, as independent researchers debated the interpretation of the data and the possibility of instrument noise. Regardless of the outcome, these findings mark a turning point. For the first time, we have the capability to search for signs of life biosignatures, on planets orbiting other stars. Within the next decade, astronomers expect to have analyzed the atmospheres of dozens of potentially habitable worlds. If we find multiple planets with atmospheric chemistry that can't be explained by non-biological processes, the case for widespread life in the universe will become much stronger. If, on the other hand, every world we examine shows only chemical equilibrium, the argument for the rare Earth hypothesis or the great filter will grow. The answer to the Fermi Paradox may finally be within reach, not through speculation, but through direct observation. But if we do find evidence of life elsewhere, a new and very human problem will arise. What should we do about it? Should we try to make contact, or remain silent? Should we broadcast our presence to the cosmos, or keep listening in cautious hope? This debate is already underway. Messaging extraterrestrial intelligence is the practice of deliberately sending powerful, targeted signals to other star systems in hopes of making contact. The logic is simple. If every civilization waits for someone else to speak first, no one ever makes contact. But the risks are unknown. We don't know who might be listening, or what their intentions might be. Announcing our presence could be an invitation, or a warning. Some scientists, including Stephen Hawking, have argued that active messaging is dangerous, pointing to the history of contact between unequal civilizations on Earth, which often ended badly for the less advanced. Others argue that it's too late to worry. Our radio and television broadcasts have already created a bubble of electromagnetic noise, more than 100 light-years across. Any civilization within that range already knows we exist. The question of whether to shout into the dark, or to wait in silence, is one of the first truly global decisions humanity faces as a spacefaring species, and it may be the most consequential choice we ever make. The debate over whether to actively announce ourselves to the cosmos or remain silent is more than just a scientific question. It's a profound reflection on who we are and how we see our place in the universe. On one side, there's the argument that if we are already visible, if our radio and television signals have been leaking into space for a century, then the risk is already taken. On the other, there's the caution that a deliberate, powerful message aimed at a specific star system is fundamentally different from the accidental noise we've been making so far. It's the difference between a whisper and a shout. No international law or treaty currently governs who gets to speak for Earth. Individual observatories, research groups, or even private citizens could, in principle, send a message to the stars without global consensus. Some targeted transmissions have already been sent, but so far, none have received a reply. The lack of coordination raises questions not just about science, but about ethics, responsibility, and the long-term consequences of our actions as a species. As our technology advances, the ability to send powerful, focused signals will only increase. High-powered transmitters and precise targeting mean that, for the first time, we could send a message that might actually be detected by another civilization, if one is out there and listening. But what should that message say? Who decides what humanity's first words to the cosmos will be? Should we send a simple greeting, a mathematical sequence, or a snapshot of our culture and biology? Or should we wait, listen, and learn more before making ourselves known? This is not just a technical or scientific issue. It's a question that touches on philosophy, politics, and even existential risk. If the universe is a dark forest, as some have suggested, then making noise could be dangerous. If it's a cosmic zoo, perhaps we're being watched, and our actions are already being observed. If we're truly alone, then the responsibility of what we do next is even greater. But there's another possibility, one that's both humbling and awe-inspiring. inspiring. Maybe the answer to the Fermi paradox is that life, especially intelligent life, is so rare that we are the only ones in this galaxy, or even in the observable universe, who have reached this point. If that's true, then our survival and our choices matter not just for us, but for the entire future of consciousness in the cosmos. If we are the first, then every discovery we make, every piece of knowledge we preserve, every step we take toward the stars, is a first step for all life. There is no one else to carry the torch if we fail. The universe, in producing us, has created something that can look back, ask questions, and perhaps one day shape its own destiny. That's a responsibility that goes beyond any individual or nation. It's a responsibility to the cosmos itself. This perspective changes how we see our achievements and our failures. Every scientific breakthrough, every work of art, every act of kindness or cruelty, takes on new weight if we are the only witnesses and the only storytellers. Our conflicts and divisions seem smaller, but our potential seems limitless. The silence of the universe, rather than being a source of fear, becomes a call to action. A reminder that what we do here and now could echo across billions of years and light years. It also reframes the urgency of the challenges we face. The 21st century is widely recognized as a critical period in human history. We are developing technologies, artificial intelligence, biotechnology, climate engineering, that could either secure our future or endanger it. The risks are real, and the stakes are higher than ever. If we are alone, then the loss of our civilization would not just be a tragedy for us, but for the universe itself, a unique voice silenced before it could be heard. But even if we are not alone, even if there are others out there, the silence we observe is still meaningful. It tells us that intelligence is rare, fragile, or fleeting. It warns us that the path from simple life to technological civilization is full of pitfalls, and that survival is not guaranteed. It challenges us to be wise, to be careful, and to think beyond our immediate desires and fears. The Fermi Paradox, in the end, is not just a question about aliens. It's a mirror held up to humanity, reflecting our hopes, our anxieties, and our deepest questions about existence. Are we ordinary, or are we special? Are we destined to be one of many, or the only ones? Is the universe waiting for us to join a cosmic community, or is it waiting for us to fill it with meaning for the first time? Whatever the answer, the silence of the stars is not a failure of science or imagination. It is the honest frontier of what any civilization can know at its current stage. It is a challenge to keep searching, to keep asking, and to keep reaching beyond ourselves. Whether life is common or rare, whether the filter is behind us or ahead, whether the silence is natural or managed, the fact remains we are here, we are listening, and we are capable of wonder. So, as you look up at the night sky, remember that the question, "Where is everybody?" is also a question about us. It's about what we choose to become, how we treat each other, and what legacy we leave behind. The universe may be watching, or it may not. But either way, the next chapter is ours to write, and perhaps, someday, someone, or something, will be out there, listening for us.